All right, let's dive into a really fascinating chemical mystery. It starts with something that looks super simple, but it ends with us uncovering this invisible exchange that, believe it or not, powers pretty much everything in our world. So, you and we're going to crack this case together. So our mystery kicks off right here. I want you to picture this scene. You've got a shiny, kind of pinkish copper wire, and we're just going to dip it into a beaker. And that beaker is filled with a liquid that is totally clear, completely colorless. It's a solution of silver nitrate. Seems simple enough, right? But what happens next? Well, that's where things get interesting. So if we just wait a little bit, the whole scene changes completely. That shiny copper wire, it gets covered in this weird, fuzzy gray coating. And that coating is actually pure silver metal. And the clear liquid? Well, it's not clear anymore. It turns this really distinct blue color. So here's the big question. Where did the silver come from, and what's the deal with the solution turning blue?
Now, this might look like a straight-up magic trick, but I promise you it's pure chemistry. To solve it, we need to figure out who the invisible players are and what they're really doing behind the scenes. This right here, this is the key to our whole investigation. It's called the net ionic equation. Basically, we've gotten rid of the spectator ions, in this case, some nitrate ions that were just kind of floating around, not really doing anything. What we're left with is the real action. Solid copper and silver ions are reacting, and they're turning into solid silver and copper ions. This is our list of prime suspects.
The secret to this entire transformation, the fuzzy silver, the blue liquid, all of it, is a secret exchange. We're talking about tiny, negatively charged particles called electrons being passed from one thing to another. This transfer, this electron shuffle, it's at the heart of everything. So let's break down exactly how it works.
The first half of this exchange is called oxidation, and it's a really simple idea. When a substance is oxidized, it loses one or more electrons. Just think of that word loss. And the other side of that coin? That's reduction. It's the exact opposite of oxidation. When a substance is reduced, it gains one or more electrons. So it's a perfect trade. One substance has to lose, and another one has to gain.
Now, how in the world do you keep those two straight? Well, chemists have this classic little memory trick that works perfectly. Just remember this. Leo the lion says grr. L-E-O, losing electrons is oxidation. G-E-R, gaining electrons is reduction. It sounds kind of silly, but trust me, it's incredibly useful.
Okay, so let's apply this to our mystery. On the left, that's copper's story. The solid copper atom loses 2 electrons and turns into a copper ion with a 2+ charge. That's Leo, oxidation. And on the right, you have silver's story. 2 silver ions each gain an electron, and they become solid silver atoms. That's Ger, reduction. And here's the cool part. The electrons copper lost are the very same ones the silver ions gained.
Okay, so we know electrons are on the move, but we can't see electrons. So how can we actually track something so small? How do we prove who's losing and who's gaining? For that, we need a special kind of bookkeeping system. And that tool is the oxidation number. Seriously, think of it just like an accounting system, but for electrons. It's the apparent charge an atom would have, and it helps us follow the electrons as they jump around. Now, it's really important to remember this isn't always a real charge on an atom, but it is an incredibly powerful way to keep score.
Now, to use this system, we just have to follow a few simple rules. And for our mystery, we really only need to focus on the first 2. Rule 1. Any atom in its pure elemental form, like our solid copper wire, has an oxidation number of 0. Easy. Rule 2. For a simple ion like silver, its oxidation number is just its charge. So for Ag+, it's +1. These 2 rules are all we need for our main case.
Let's do a super quick practice round, just to see how this works with a molecule like carbon dioxide, CO2. Okay, so we know from our rules that oxygen is almost always a -2. And we've got 2 of them, so that's a total of -4. The whole molecule is neutral, which means its total has to add up to 0. So, what number balances out in -4? +4, right? So carbon's oxidation number in CO2 has to be +4. See? Simple as that.
So now that we have our tracking system, we can introduce the final characters in our story, the agents. You see, in every electron exchange, there's a substance that causes the oxidation and one that causes the reduction. It's time to identify the culprit and the victim in our little electron heist. Now, this can feel a little backwards at first, so just stick with me. The oxidizing agent is the one that does the oxidizing, meaning it's the one that takes electrons from something else, and by taking electrons, it gets reduced.
Then you have the reducing agent. It's the one that does the reducing. It gives its electrons to something else, and in the process, it gets oxidized.
All right, let's head back to the scene of the crime. We have our net ionic equation, and now we have all the tools we need. We've got Leo says jur, we've got oxidation numbers, and we've got our agents. Let's put it all together and finally solve this thing.
And here is the hard evidence laid out for you to see. Take a look at copper. It starts out as a solid element, so its oxidation number is 0. It ends up as a 2+ ion, so its number is now +2. Its number went up, that's because it lost negative electrons. Now look at silver. It starts as a +1 ion, and it ends as a solid element with an oxidation number of 0. Its number went down. It was reduced.
And there you have it. The case is officially closed. Copper's oxidation number went up from 0 to +2, so it was oxidized. And because it gave away those electrons, the solid copper was the reducing agent. The silver ion's oxidation number went down from +1 to 0, so it was reduced. And because it took the electrons, the silver ion was the oxidizing agent. That's the whole story.
Now, why does solving this one little mystery even matter? Well, because this isn't just some neat trick you do in a lab. This exact same process, this electron shuffle, is happening all around you and even inside of you, right this second. It literally powers our entire world. I mean, just think about it for a second. Getting pure metals from a rock? That's a redox reaction. The slow rusting of a car? Redox. The power coming out of a battery? That is a super-controlled electron shuffle. Even the most fundamental things in life, like photosynthesis, where plants make their own food, and respiration, where our bodies burn food for energy. It's all just an incredibly complex chain of redox reactions. So we started with just a simple copper wire and ended up at the very core of how both life and technology function. It really leaves you with a final thought, doesn't it? If our entire world runs on this invisible electron shuffle, what other hidden chemistry is out there shaping our reality every single moment? Thanks for joining me.